Okay, and without further ado, we'll go ahead and get started. This is our Wi-Fi 101 webinar. So this is more of a sort of in-depth look at some of the nuts and bolts that make Wi-Fi work. One thing I found over the years is a lot of people out there, even if they've installed a lot of different Wi-Fi products, a lot of them don't really understand what's going on in the back end. So this webinar is designed to sort of try to shed some light on some of that stuff. So we will start here with just going over a little background on Zyxel. So Zyxel has been around making computer networking equipment for over 30 years. We got started all the way back in 1989. These days we have over 100 million devices deployed out in the field, and we serve 150 different global markets. Here in the U.S., we are based out of Anaheim, California. So that's our sales office, marketing, tech support, and our warehouse. So when you call in to get help from Zyxel, you are getting help from Zyxel employees here in Anaheim. For those of you on the East Coast, if you call in early in the morning, you will be getting help from our German tech support team. But between 8 and 5 Pacific time, you are dealing with Zyxel employees here in Anaheim. So we'll start talking a little bit about Wi-Fi. So we'll start with some of the very basics. There's 3 different groups out there which play a big role in defining what Wi-Fi is. So the first one is IEEE, right? The International Electrical Engineers Group here. So they create the standards. That's where you'll see 802.11 A, B, G. The 802.11 and that letter refers to the IEEE standard that the IEEE group has put out. The Wi-Fi Alliance is a group of chipset vendors and hardware manufacturers that get together, and these serve 2 purposes. First one is these certify products for compatibility. This was a big problem back in the early days of Wi-Fi, where there's enough left open in the IEEE standards that different people can interpret things different ways, implement them differently, and sometimes that causes compatibility issues. So the Wi-Fi Alliance came together to do compatibility testing, and they still do that today. They are also a big marketing group for the industry. They are the ones that decided to rebrand 11N, 11AC, 11AX, and start calling them Wi-Fi 6, Wi-Fi 5, Wi-Fi 4, etc. So that's the role they play. And then there's the FCC, right? That's the U.S. federal government. And these set up the rules as far as channels that can be used, power output, and a number of other different things and behaviors when it comes to Wi-Fi. So the 3 of them working together is what gives us Wi-Fi as we know it and use it here in North America. So now we'll talk a little bit about what makes Wi-Fi work. So Wi-Fi is using radio waves. Right, so the same thing as what you would use for a walkie-talkie, what you use for a wireless mouse, what you use for radio and over-the-air TV. So just some basics here. As a general rule, as frequency goes up, more data can be crammed into it. But also as frequency goes up, the signal doesn't go as far. It degrades much quicker with higher frequencies. So I put down there, cordless phones. So that's for those of you that are older like me and have lived through sort of the evolution of cordless phones, you've experienced that. Back in the day when I was younger, cordless phones were operating in the 900 megahertz frequency. So it's a very low frequency. Sound quality was okay. But you could really go far with those phones. I remember being able to, take the phone outside, walk across the street, and still be able to maintain a phone call with the, the base headset or base set, whatever, back in the house. And then there was a push in, I want to say, the early 90s, maybe late 80s, to 2.4 technology. So one of the problems with 900 megahertz is there's not a lot of spectrum available. So if you lived in a condo or an apartment building, you would get interference. You would be able to hear other people's calls. So they moved to 2.4. So 2.4 is a much higher frequency. It allowed better call quality. There was a bigger chunk of spectrum available, so you could have more calls without interference. But the downside was the phone now, couldn't go as far. You could no longer cross the street and maintain your phone call. And then by the early to mid-90s, there was a big push of moving people to 5 gigahertz. So 5 gigahertz opened up even more spectrum. So again, it helped with those dense situations, like apartment buildings and condos and things like that. But it gave you better sound quality. But again, the range wasn't as good. And I know some of my friends who had bigger houses, you know, there were issues where some rooms you couldn't have a wireless phone call because the signal couldn't reach all the way back from the headset back to the base station. So it just so happens to be 2 of those 3 frequency bands we talked about are the ones used by Wi-Fi, 2.4 and 5 gigahertz, the same channels used by your old cordless phones, are the same ones we use today for Wi-Fi. So that's because radio frequencies themselves are regulated by the FCC, and for the most part, if you are going to be broadcasting radio frequencies, you need to have a license with the FCC. So you lease that spectrum, you get a license, and you agree to follow their rules. So the FCC over the years has opened up chunks of this spectrum to home users and other people who don't have a license. So that's 900 megahertz, 2.4, 5 gigahertz, and now some of the 6 gigahertz frequency spectrum. So because that's available for everyone, that's what everything uses. So in general, 900 megahertz just doesn't have enough bandwidth available, so you don't see a lot of people using it, and just the low frequency, you can't cram a lot of data. So these days, almost anything that's using a wireless technology in your home or business is using either the 2.4 or the 5 gigahertz spectrum. So when we're talking about radio waves, we want to talk a lot of times about power. So power coming out of your device is measured in dBm, decibel milliwatts. However, you will often see just plain old milliwatts being used. And historically, you would see milliwatts being used on consumer equipment, and you would see dBm or dBi being used on business-grade equipment. So why is that? And the answer is generally marketing. So if you're marketing towards end users, milliwatts seems a lot more, creates a lot more better marketing terms. So when it comes to dBm, every 3 dBm increase doubles the power that's coming out of the device. So if you go from a 20 dBm device, here we go, right, that's equivalent to 100 milliwatts. So if you go from 20 to 23, it doesn't sound like much. But if you convert that to milliwatts, you've doubled your power from 100 to 200 milliwatts. So when it comes to consumer equipment, small changes in dBm can appear to be much larger to the end user. So you're saying, well, why didn't we do that a lot on the business grade equipment? And so part of the problem, especially in the old days when it comes to Wi-Fi, is that it was very common for people to remove the antenna that came with the device and replace it with another antenna. And those antennas are measured in dBi. So that's the antenna gain. And you can take the dBm, add the dBi, and easily calculate your total output power. In addition, if you're doing things like outdoor point-to-point links, you can very easily calculate your signal loss and things like that, since all the formulas will use dBm and dBi to measure and calculate everything. So in the early days of Wi-Fi, there was a lot of that going on. These days, most access points don't allow you to plug in different antennas. The antennas are hardwired into the device. And the technology itself is a lot less fiddly. The output powers tend to be higher. So you don't see people necessarily needing to use dBm and dBi a lot unless you're just looking at the data sheet for 2 products doing comparisons. But it used to be a pretty big factor when it came to doing Wi-Fi deployments. So another term you will hear used a lot, and this is one that probably doesn't get talked about enough, is the signal-to-noise ratio. Signal being the radio frequency or the radio transmission that you want to hear versus the level of noise also on that same frequency. So a good analogy to this would be having a conversation with somebody. If you are sitting across the table from somebody in an empty restaurant, you have really good signal-to-noise ratio. You can hear the other person. There's not a lot of background noise. Take that same scenario, move it to 11 o'clock at night when now this restaurant has turned into a nightclub, and now you've got a high level of noise and you've got a poor signal-to-noise ratio. And the signal-to-noise ratio is like the number one thing that comes into play when it comes to how fast your Wi-Fi connection is. And then just attenuation, basically saying your signal drops off. So the farther the signal goes from where it's being transmitted, the weaker the signal becomes. It will drop off much more quickly when it's passing through a solid object versus something like the open air, but it does drop with both. So we've got here for you the formula. So if you really want to know how far does this access point going to be able to transmit the signal, this is the formula you need right here. So it's not an easy formula to use, but that's what you would use. You plug in your numbers here, you know, and it would tell you how much loss you're going to get over that. And that's assuming it's open in the open air. So distance is what the D is here, F is your frequency, 2.4 or 5. Plug it all in together and it'll tell you how much loss you're going to have of the signal. And then here's just some rough guidelines here for common objects we're going to encounter out there in the real world and how much they are going to degrade the signal. So a standard window can drop you 3 dB, right? So having your power as it goes through that window. A tinted window, something that's got one of those metal layers on it, that's designed to, you know, keep out infrared, darken the window a bit, that can give you up to an 8 dB loss. So pretty big losses. And then the walls here, 10, 15 to 20. So this is something that we've encountered in the real world, is that sometimes it's actually better if you're trying to shoot a link between two buildings or provide outdoor coverage from an indoor AP. Sometimes it's actually better if you've got like stick-built construction and you don't have a lot of insulation. It's better to mount the AP on the wall rather than mount it on the window looking out, because sometimes the window will actually degrade the signal more than a thin wall. So another thing I want to talk about here is when it comes to Wi-Fi range, is that, you know, it's a combination of a lot of factors. It's things like your signal strength, the signal-to-noise ratio, attenuation, the frequency being used, all those things we talked about before. And another one, just really quickly to bring it up, and I probably should have mentioned it on the previous slide, is, you know, water absorbs RF frequency. So this is something we run into a lot with people who are doing outdoor Wi-Fi deployments, RV parks, things like that, is they will go out there one time of the year, say during the summer when it's sunny out, it's not too humid, and everything will work great. And then when the rains come or when the snows come, suddenly they can't make those connections anymore. So why is that? It's because the air has more moisture in it, and so therefore the air is absorbing more of the signal than it was previously. So it's something else to keep in mind. Also things like trees, right? Trees are basically just, you know, giant sacks of water, especially, you know, leaves and things like that. So you'll get different RF performance at different times of the year based on how much leaf coverage there is on nearby trees. So just things to keep in mind when you're dealing with outdoor wireless. But the main thing here for this slide is we need to keep in mind that Wi-Fi is a two-way communication. So the distance, the range you're going to get, is primarily going to be dictated by the lowest or the weakest member in that two-way conversation. So here you've got your typical business class access point. It's going to probably have at least 500 milliwatts of output power. And I know I'm not using dBm here, but by comparison, a typical 4G or 5G phone, the Wi-Fi chip in there is probably only putting out at max about 25 milliwatts. So you see there's a big power imbalance between the two. So you can be a long ways away from that AP and still be able to pick up the signal, but the AP isn't going to hear what you send back. And when we're doing stuff like TCP, right, your AP sends data and waits for the device it's talking to confirm it received the data correctly before it sends the next bit of packet. So if your AP can't hear the device it's connected to, it really hurts the signal and limits your range. So again, just going back to our analogy here, it would be, you've got two people having a conversation, but one of them has laryngitis, right? So even though one person can shout really loud and you can hear them, all the way across the building, They can't have a conversation with their friend with laryngitis because they can't yell louder. So they have to get closer together to be able to have that two-way conversation. And this causes a very common problem we run into with Wi-Fi deployments, where somebody is using a phone or a tablet or something like that, and it shows pretty decent signal strength. It's got 3 bars of signal strength or 2 bars of signal strength, but the Wi-Fi isn't working, or it's working really, really poorly. So why is that? It's because the phone or your tablet is telling you how strong the signal is that it is hearing from your access point or your router. It has no way to know whether or not the signal it's sending back is making it there or not. So what happens is the phone sees a nice strong signal from the AP, but the signal isn't getting back to the access point, and that's why the Wi-Fi isn't working, even though your device seems to indicate that you've got a decent signal. So another thing we want to talk about here is just RF behavior. You know, we call them radio waves, we use the term waves, and you know, waves in water are a very good analogy for how RF waves work out in the real world. And it's important to understand some of this because oftentimes these type of issues are the cause of problems you're having on your Wi-Fi network. And it's really hard to troubleshoot, right, because you can't see those radio waves and see what they're doing. So, you know, think about this transmitter here. This is your, in this case, it's a laptop transmitting back to an access point. But think of that here as just like being in a pond and throwing a rock in the pond and watching the ripples as they emanate out. You know, if they hit something like a solid wall, they'll stop. In the case of RF, they have the ability to pass through, but they will, you know, degrade the signal quite a bit, and the signal may become fuzzier. But some of those waves will then, you know, wrap around it and go around the device. They can wrap around the device or wrap around the obstruction. If they hit something, they can reflect off of it, just like water waves do. Certain sorts of materials, they will cause multiple ripples or multiple reflections to take place. So just something to keep in mind. Now you're saying to yourself, you know, how does Wi-Fi work? How do devices know when they can transmit and send signals? So one thing to keep in mind when it comes to Wi-Fi is in reality, only one device on the network can transmit at a time. So each device has to take turns using the available frequency. If 2 or more devices transmit at the same time, it causes interference, and in general, it's going to cause those packets to be dropped. Now, Wi-Fi, the way it works, was really first standardized all the way back in 1999. And until Wi-Fi 6 came along, there really haven't been a lot of significant changes to the very basic core of how Wi-Fi functions. And even with Wi-Fi 6, we've made a number of changes, but obviously a lot of the devices that will be connecting to your Wi-Fi 6 AP probably don't have Wi-Fi 6 chips in them, or just have Wi-Fi 6 Lite chips that don't have all the features. So they're still going to need to be operating and are still going to run into those same issues with Wi-Fi 6 that you had with all the previous generations of Wi-Fi. So this right here is basically the diagram of the logic of how a device determines whether or not it can broadcast. So basically, it senses the medium. It listens to see if anybody else is broadcasting, right? If somebody else is broadcasting, uses a random number generator to determine how long to wait, and then it'll start the process again after that time has gone by. So if it sees that nobody is broadcasting, then it decides to send its data. So this can cause problems, right? As you add more and more devices onto your network, you're going to increase the likelihood that 2 devices are going to decide they need to send data. They're both going to listen, nobody's broadcasting, and both will decide to broadcast at the same time, causing the collision and causing those packets to drop. The other thing here is, again, is you've got all these devices, and if they hear somebody else broadcasting, they use a random amount of time before they check again to see if they're okay to broadcast. So what that also means is you get inefficient usage of time, right? Because one device will stop broadcasting, but the other device that needs to broadcast is still waiting for that random amount of time before it decides to check to see if it can broadcast again. So it ends up with us poorly utilizing the available airtime on the frequency being used. Another related problem here is what we call the hidden node problem. So here's your access point in the middle of the slide. You've got two different client devices that are connected to that access point. The range from that access point is this big blue circle. So both devices are within that blue circle. The yellow circle here is how far this device can transmit back. So it's within range of the access point, and the access point is within range of anything that device transmits. The problem you run into is this device here. It also is in range of this access point. This access point can hear anything it transmits, but these devices don't overlap, so they can't hear each other. So we now run into situations where these devices will both sense the medium and determine that nobody else is broadcasting because they can't hear anything. And so both will transmit at the same time. The access point will hear them both at the same time. And most likely, either only one of them will be heard, or more commonly, the packets for both will be dropped and they'll have to try to retransmit. So that's what we call the hidden node problem. So now I want to define some terms here which cause some trouble for us in the industry. And part of the problem is these terms are sometimes used interchangeably, and there is no hard, firm rule for how they are used. So I'm going to start with what we call the data rate, or what I most commonly will refer to as the data rate. You will sometimes see this on data sheets or spec sheets being called a physical rate or a link rate. So this is how fast your device can send data to the access point, or vice versa. So this is how fast that connection is between the two devices. And it includes not only the data that you want to send, but it also includes all of the Wi-Fi protocol overhead that goes into making that connection possible. So when you're talking about something like Ethernet, there's very little overhead. So the data speeds that you can see if you do like a speed test are going to be very, very similar to what you see on the data sheet as far as the stated speed, that physical rate or the data rate. You know, the problem we run into here, though, is because the Wi-Fi has a lot more overhead, is that when people do a throughput test, you know, they use speedtest.net or Ookla or something like that, that's not measuring all of the data being sent. It's only measuring the data you want to send. So it's downloading a file from a server or uploading a file to a server and measuring how long it takes to go. So because of that, this throughput, as it's commonly referred to, when it comes to Wi-Fi, can be as much as 60% lower than the data rate that you are actually connected at, because the data rate includes overhead. Throughput tests do not. So that causes a lot of negative reviews. You can pull up any wireless device on Amazon and you will see a lot of people complaining. You know, I bought an N300 device, but I can only get 100 megs throughput. You know, and unfortunately, the use of the data rate is the industry standard is set by IEEE. So that's what people talk about. You know, it's what you will see on the data sheets, that's what you'll see on the product listings. But the throughput is almost always going to be, you know, anywhere from 40 to 60% less, depending on your environment. And that's another thing that goes through here. The speed you're connected to, you know, the maximum speed of that access point may not be the actual speed that you can achieve. Maybe you're too far away from the access point. Maybe there's a lot of RF interference. Maybe your access point, that speed is based on being able to support 3 spatial streams, but your laptop can only support 2 spatial streams. So there's a third of the maximum speed cut right there before even taking into account overhead issues. So that's things to keep in mind, and that's why you see a big difference between the advertised rate on the spec sheet and what you will see if you do some sort of speed test on a connected device. Which leads us to, how do I increase speed? Now this is being done from the point of view of a hardware manufacturer or from the IEEE setting the standard, not you yourself out in a real world deployment. So when it comes to increasing speed of devices, there's 3 main ways that we've increased speed over the years as we go from, you know, 802.11 to 802.11a, b, g, n, etc. So one is encoding, what we call QAM, 64-bit QAM, 256 QAM, and now with Wi-Fi 6, 1024 QAM. So that's basically how much data can be crammed into a chunk of airtime spectrum on a frequency. So you're saying, well, why didn't we just start with 1,024 QAM? And then the answer is basically, it's a power to horsepower ratio type issue. You need chips that are powerful enough to be able to do this high bit rate encoding, but also low enough in power demand that you can put those in a mobile phone or a tablet without it killing the battery. So it's taken a while for the chips to evolve to the point where you could use these higher end QAMs to cram more data into the available airtime. The other one is spatial streams. So this is how many streams of data can be sent simultaneously, or it can be received simultaneously. We'll talk a little bit more about it here on an upcoming slide. And the other one is just by increasing bandwidth. That's a big one. So, 11G used 20 megahertz channels. 11N, a big part of the way 11N got its speed increases was by doubling the available bandwidth. Essentially, you double the bandwidth you were using, you double the amount of data that you could send at a time. Then with 11AC Wave 1, we added the ability to do 80 megahertz channels, and Wave 2 of 11AC and now Wi-Fi 6 can use 160 megahertz channels. So that's a big part of where those speed increases come from. And this is leading us to one of the challenges with using those bigger chunks of spectrum. So we'll start here by talking about the 2.4 gigahertz spectrum. The 2.4 gigahertz spectrum here in North America is only approximately 60 megahertz in size, whereas a 20 megahertz Wi-Fi channel is 20 megahertz. So you only have 3 devices or 3 different networks that can be operating at a time without causing interference to each other if you are using 20 megahertz channels, right? You've got 60 total available and you can only split it up 3 ways. But again, we talked about when we went from G to N, the big way we got the increased advertised speeds was by doubling the bandwidth of those channels from 20 megahertz to 40 megahertz. And again, there's only 60 available. So that means as soon as you add a second device, you will have overlap between those 2 different devices, and you will have issues caused by co-channel interference, right, as those signals sort of cancel each other out if you've got 2 devices on different APs broadcasting at the same time. So to really take advantage of those 40 megahertz channels, it really only takes place in a home environment where you've got a big space between you and another access point. It doesn't work too well in a business case or apartments or condos where you've got a lot of access points within a relatively small area. So that's why there was a push starting with 11N to move people to using 5 gigahertz radios. We saw it with 11N, and as time went on, more and more 11N devices were dual radio, and then 11AC, pretty much anything 11AC and Wi-Fi 6 will be using 2 radios at 2.4 and 5. And that's because 5 gigahertz opens up a lot more channels for us. I think it's 26 20 megahertz channels that can be used. Right, so the benefit here is you've got a lot more devices can be used in the same area without causing co-channel interference with each other. The downside is, of course, as I mentioned earlier, as you go up in frequency, the range, how far that signal can go, lessens. So that's kind of been the trade-off over the years. But one thing I want you to notice here on this chart of all the different channels available is a good chunk of these are highlighted in orange and labeled DFS channels. So what is that? Basically, the 5 gigahertz spectrum, before it was opened up for everybody to use without a license, was licensed spectrum. You had to have, so what happens when, the FCC comes along and says, okay, we're now opening this up to everybody to use, the problem is people who are already using that frequency and had been for decades said, well, wait a minute, what about us? You're going to cause problems with our existing solutions. So that was the FCC's solution, was something called DFS. And basically for Wi-Fi devices, they put into effect a group of rules with what needs to be done in order for a Wi-Fi device to operate on these DFS channels. And the short version of it is before an AP can broadcast on a channel and start using one of these DFS channels, it has to listen for, I think it's 30 seconds, could be wrong, but I think it's 30 seconds, and verify that there are no legacy devices using it. And then it can start using those channels. But then the problem is, if it then later detects a legacy device using those channels, it has to stop broadcasting. So it can either then switch to a non-DFS channel, or if it switches to a different DFS channel, it has to pause and listen and verify that other channel is not being used before it starts using that channel. In addition to that, when it comes to FCC certification, it can easily add 6 months into the certification process. So because of that, a lot of consumer equipment does not support DFS. And even on the business side of things, often when products come out, when they first ship, they don't support DFS, and then DFS is enabled in a firmware or software update down the road. So for those two reasons, a lot of people don't want to use those DFS channels. Maybe you've got people, bringing devices from home, and those home devices don't work. Or you have people complaining that they keep getting kicked off the network because you've either got a legacy device nearby, maybe you're near an airport, or maybe there's just a nearby piece of industrial equipment which is putting off RF noise in that channel, and your access point sees that and just assumes it's a legacy device. So you get kicked off periodically. Especially in hospitality. This has been a problem in hospitality deployments where they'll, by default, be using these DFS channels, and a lot of the guests will be, bringing their tablets from home that don't support DFS and they can't connect to the network. So because of those reasons, a lot of people choose not to use these DFS channels. So if you don't want to use DFS, you go from 26 available 20 megahertz channels down to, I think it's 9 available DFS channels. But again, that's 20 megahertz channels. As we talked about before, starting with 11N, what was that, 10, 11 years ago? We were using 40 megahertz channels to get the advertised speed you would see on the data sheets and on the product box, right? So if you're using 40 megahertz channels, remember with 2.4, basically you can only use one, and as soon as you added the second device, you would have interference. With the 5 gigahertz spectrum, you can have 4 devices operating at 40 megahertz without having any sort of interference between them and overlapping the RF that they're using. But again, we increase speed by increasing bandwidth. So with 80 megahertz channels, if you're using those, and by default, just about every device is using 80 megahertz channels out of the box, you've only got 2 non-DFS channels that you can use before you start getting overlaps. Only 2 devices, 2 access points that you can have operating before you start having issues. And then there's the 160 megahertz channels, and those have to use DFS. Because of their size, there is no chunk of non-DFS spectrum that's 160 megahertz in size. So those all have to use DFS. So the good news is that means most products that are Wi-Fi, advertising Wi-Fi 6 support will support DFS channels. So that's it as far as bandwidth goes. The next one I want to talk about here is spatial streams. So, as we talked about before, when you broadcast out these radio waves, they react to the environment and can bounce off of things, they can wrap around things, they can do all sorts of really weird stuff. And that used to cause problems back in the 11BGA days. It was what we would call multipaths, and it was the bane of existence for people trying to troubleshoot Wi-Fi environments. Because what happens is your transmitter here sends out a signal, it radiates out as essentially a circular pattern, just again like the waves coming off of a rock thrown into a pond. So the signal you're sending, most direct way, will go straight out and hit the device that's trying to listen. But the signal will radiate out, it will hit various objects in the environment and bounce off of them. And because the path that those signals are taking are slightly longer than the path that's direct, it creates what would, in auditory terms, be an echo, right? I mean, this is exactly what causes echoes in rooms, right? You talk, and the sound bounces off of different parts of the room, and echo replies back to you. It's the same sort of thing, only with radio frequencies here. And so it caused this echo effect, which we would call a multipath. And then starting sort of with 11N is people started figuring out how to take advantage of these multiple paths and instead of being a problem, turned it into a benefit. And that's where we come up with spatial streams. And that's basically the ability to take these different paths of data that are being broadcast or are taking and be able to split them up and identify them. So the way we do that is basically we have each antenna on our device broadcast a different set of data at the same time. So in this case, imagine we've got two different antennas here that can actually transmit. So we can send two different 150 megabit streams simultaneously. Each stream, because the antennas are spaced apart, will follow slightly different paths in the real world environment and will arrive slightly offset at your listening device. And it will be able to take advantage of that to differentiate those two signals and combine them together into one 300 megabit signal. Now we can also use this as something we call MIMO, Multiuser MIMO. So instead of taking these two streams together, sending them to one device and combining them together, we can take advantage of the RF paths and send different streams of data simultaneously to different users on the network. So each of those spatial streams is going to a different device. So instead of having one device with a 300 megabit connection, you can have two devices simultaneously with a 150 megabit connection. So with 11AC and earlier technologies, multi-user MIMO was only from your access point or router to the client device. With the Wi-Fi 6, you now have the ability to do MIMO in the other direction as well. So when it comes to spatial streams, you will see this on business class products on the data sheet. So that's another thing that's different between consumer products and business products. We talked earlier about how consumer products tend to use milliwatts to talk about output power, where business products use dBm. Same thing here when it comes to spatial streams. Business class products generally will put the number of spatial streams on the data sheet, where consumer products won't mention spatial streams at all. They'll just tell you the maximum data rate that the device is capable of. They'll say, N300, AC 1800, whatever it happens to be, which is basically taking the max data rate per spatial stream and adding them together on consumer equipment. Where the business stuff, we just tell you the spatial streams and let you figure out the math to the total maximum speed. So when you're looking at the data sheets, you will usually see the spatial streams reflected as two numbers with an X between them. The first number is how many spatial streams the device can transmit, and the second number is how many spatial streams the device can receive. So generally when we're talking about routers and access points, these numbers will be the same. If it can transmit two spatial streams, it can receive two spatial streams. If it can transmit three spatial streams, it can receive spatial streams. However, client devices are not always symmetrical like this. It is very common for phones and laptops and things like that to be able to receive more spatial streams than they can transmit. So you will often see 1 by 2. It can receive two spatial streams from your access point, but when it transmits back, it can only use one spatial stream. So the signal from your client device to the AP is half the speed of the connection from the access point to that client device. So you'll see 1 by 2, 2 by 3, even sometimes 1 by 3, stuff like that. So just keep that in mind that you can have this mismatch as far as speeds in each different direction because of that spatial stream support. Now there is one exception to this notation, which is primarily you'll find it on Cisco equipment. And you will see something like this here. I know it's small text, but it's 4 by 4:3. Right? So when you first see that, your first thought would be, oh, that's 4 spatial streams, 4 by 4, 4 transmit, 4 receive. But the key here is that number after the colon. What the colon is telling you is actually how many spatial streams can be used. So while you've got 4 antennas for transmitting and 4 antennas for receiving, the chip can only actually listen or transmit on 3 of those at a time. It's mostly a marketing thing to make people think it's faster than it is. There are cases where being able to rotate and choose which, 3 antennas of the 4 you're actually using can maybe help you out as far as, choosing the best 3 for a little bit better signal strength. But it's a really minor effect usually. So to combine that all together, we've got this little chart here. First column is how many spatial streams are supported. Second column is the modulation type. So something to keep in mind when it comes to the modulation is the modulation that you can use isn't just defined by the chipset. For instance, right, 11AC can support 256 QAM, but the signal to noise ratio has to be good enough that you can support it. So it's very common if you're farther away from the access point for it to drop to 64 or 16-bit QAM based on the quality of that connection, and then just how much bandwidth you're using. So when you're looking at data sheets and product boxes and they're talking about maximum speed, they're going to assume the maximum number of spatial streams, the maximum possible encoding type that the device supports, and the maximum available bandwidth. So just something to keep in mind. Because in the real world, you may not be able to use the fastest modulation type. Your client device may not support the maximum number of spatial streams. Due to RF considerations, you may not be able to use the maximum amount of bandwidth. So you'll see lower speeds just from that. So another common question we run into is, well, how many devices can I get on this access point? How much do you support? And I'll tell you right now, ignore what the data sheet says. The data sheet means nothing. The limitation in the real world for how many devices you can have connected has more to do with the RF environment and the Wi-Fi technology being used, 11AC, Wi-Fi 6, etc., than anything that the hardware supports. So you will, unless you're using really cheap access points, you will have significant performance issues due to RF crowding and utilization long before you get to the maximum number of client devices you see on that data sheet. So the limitation is the Wi-Fi protocol itself and the real-world environment, not the theoretical maximum you see on the data sheet. The data sheet is basically telling you how much memory they've assigned to the association table. How many entries can it support at a time? So I'll sort of give you a real-world example of this here, or a simulated real-world example. So in this scenario, we have users, and these users are connected to your access point, and they are trying to watch a 3 megabit live stream. We'll call it a Zoom call. They're trying to make a Zoom call, and between the audio and video, it needs 3 megabits for each connected device to support that. So in this scenario here, we are using 20 megahertz channels, 5 gigahertz frequency, and all the client devices have the same signal strength. So what we see here with our laptop scenario, so this is a laptop, it's got a good Wi-Fi chip, it supports 3 spatial streams, as does our access point. So with this, you can get 34 devices on there reading a 3 megabit stream without any issues. As soon as you get above that, there's not enough bandwidth available for everybody to have a 3 megabit stream, and you will start having degradation and people complaining about the quality of your Wi-Fi. It doesn't matter that this access point in theory can support 512 associated devices, because once you get more than 34, the Wi-Fi performance starts causing issues and complaints. So now we're going to switch to a tablet, and in this scenario, the only difference between the tablet and the PC is how many spatial streams the built-in chip supports. So all we're doing in this scenario is removing a single spatial stream. This can only support 2 spatial streams. And now we've gone from 34 connected devices using Zoom, so we can only get 21 devices on there using Zoom before we start having complaints from the users that there's not enough bandwidth to support their streams. Same scenario, but now we go to a mobile phone that only supports 1 spatial stream, so it's a low-end Android phone. Again, nothing else has changed except for the number of spatial streams supported. And now you can only have 10 connected devices watching that 3 megabit Zoom stream before your users will start complaining about poor Wi-Fi performance. And so this is just dealing with how the available bandwidth and airtime is being used. And of course, in the real world, there's a lot more stuff that's going to go into it. You know, people are going to have different signal strengths. You're going to have a mix of different spatial streams. You know, you'll have a mix of different applications. But that's just showing you how just one factor here, the number of spatial streams, can make the difference between 10 devices or 34 devices on the access point before users start complaining about quality of the Wi-Fi connection. So I talked about it a lot before, which was co-channel interference. This is a quick reminder. This is basically, you know, when it comes to Wi-Fi, only one device can transmit at a time. If 2 or more devices are transmitting at the same time, it normally cancels itself out and results in what we call co-channel interference. If you used analog walkie-talkies back in the day when you were a kid like I did, you know, I don't know if they're still available these days or not. You know, you would run into this with your friends if you had a group of friends with walkie-talkies. If 2 or more of them tried to talk at the same time, you would just get a horrible, horrible noise trying to listen to it, and you couldn't make it out. It's the same thing with Wi-Fi and co-channel interference. And of course, in addition to other Wi-Fi devices, as I mentioned before, you know, pretty much anything wireless these days is using 2.4 or 5 gigahertz. So they can be non-Wi-Fi wireless devices, but they could still be causing co-channel interference. Plus, various industrial devices can be putting off RF noise. Microwaves use 2.4 to heat up food, for example. So the traditional way of managing co-channel interference is you would spend a lot of time, you would do what was called a site survey. You would go out with some access points and a laptop and a device to measure signal strength, and you would try to figure out where each of your devices should go, and then you would plot out which channel each device would use to try to space out the devices as far as possible from each other. Another common thing you would do is you would turn down the power on the access point to reduce the overlap. Because as we talked about before, right, these access points are generally much more powerful than the connecting device. So while the range from your phone to the access point may be 100 feet, that signal is actually going, you know, 500 feet. So you would reduce the signal strength, therefore you would reduce the co-channel interference. The trade-off is, though, is now your signal-to-noise ratio gets less. So you're trading one cause of wireless performance issues with another cause, which is poor signal-to-noise ratio, because the signal now is much weaker. So another solution to this problem is smart antennas. So not all of our APs come with smart antennas, but many of our models have this available on them. And most of our APs are available in a smart antenna and non-smart antenna configuration. So basically what smart antenna does is, rather than having one fixed antenna pattern, which most access points have, let's just have one antenna, we have this smart antenna that's able in essentially real time to go through hundreds of different antenna patterns and choose the best antenna pattern for that client device. Now, our algorithm not only looks at where that client device is in relationship to the access point, but we also look at other sources of RF noise and choose a pattern that allows us to essentially ignore or not hear that interference. So one of the nice things with smart antenna versus something like beamforming is smart antenna works with mobile devices. So as devices move around in the environment, smart antenna is essentially in real time able to change the antenna pattern that it's using. So we've got a case study here. So this case study was a hotel environment. We're using our wall plate APs. So these are lower powered access points, and you put one per room. We're using the 5 gigahertz channel, so the signal doesn't go very far. It gets absorbed by walls pretty quickly. It's lower powered, and we've got a number of different non-DFS channels to choose from here. So there is no 2 APs next to each other using the same channel. So for this comparison, we used our product, the NWA1302AC. That's now been EOL'd, so the replacement with smart antenna is the WAC 5302D-SV2. It's essentially the same product, but it's got nebula management support and controller support. And we compared it to a Ubiquiti, which is almost identical product, same form factor, roughly the same output power, but does not have smart antenna technology. So we tested these out. So to start with, we had one AP operating. We have two client devices connected to that AP. In this test, you can see the aggregated throughput with our smart antenna, 404 megabits per second. Ubiquiti, 406. So technically, Ubiquiti beat us. Airtime utilization was essentially the same, 67% between both our product and the Ubiquiti product. Now, as soon as we add a second access point using that same channel, again, not right next door, it's either several rooms down or up on a different floor, we start noticing the benefits of smart antenna technology. So you'll see now our aggregated throughput is now 785 megabits per second, whereas the aggregated throughput here on Ubiquiti is 555. So basically, smart antenna is allowing multiple devices to transmit to their associated access point at the same time without interfering with each other, because the smart antenna is able to ignore a lot of that overlap. And you'll see when it comes to channel efficiency, Ubiquiti is using 95% of the available airtime. We are able to achieve more than the maximum theoretical 100%. We're able to achieve 131% of the available airtime. Why? Because again, the smart antenna is allowing these different APs and the different connected devices to transmit at the same time without canceling each other out by choosing antenna patterns which don't hear the competing devices for that airtime. So same test, but now we've added a third AP, and again, none of them are next to each other. And you see the same thing. Now the aggregated throughput is over 900 megabits per second on the smart antenna APs versus the Ubiquiti without smart antenna, where it's still pretty much maxed out there at, under 600. So again, if we look at airtime, we see airtime utilization has gone up. So it's gone up when it comes to airtime utilization. We're now up to 155% of the theoretical 100% maximum, and the Ubiquiti's actually dropped down to 91% maximum or utilization of the airtime, just due to, as we talked about before, the inefficient ways that Wi-Fi determines whose turn it is to broadcast. Another really key thing here is you'll notice when it comes to the bandwidth, with smart antenna, each AP is essentially getting around the same aggregated individual throughput. Where with the Ubiquiti without the smart antenna, you see there's some pretty significant differences with which AP is getting the available airtime. So those are the benefits of smart antenna technology. Next up here is something that we have here at Zyxel called dual optimized antennas. So again, your standard access point, including some of Zyxel's access points, are designed to be mounted on the ceiling centrally, and they radiate out a circular pattern. So that's what 90% of access points do. They have that one antenna pattern. But in the real world, oftentimes you cannot mount these APs on the ceiling. You end up mounting them on the walls. So because of that, the coverage pattern is less than ideal. You don't get the range on the floor that you would like. And if you're in a multi-floor building, you run into interference issues between floors because now you're sending a lot of the signal up and down into the floor and ceiling. So Zyxel offers on some of our models what's called dual optimized antenna. So we've got, it's not smart antenna, but it's also not the singular antenna. It's now got two different sets of antennas. One that's optimized for ceiling mount, one that's optimized for wall mount. So you can choose which of the two to use based on where you've installed that particular access point. So now just some general tips. Most APs are designed for ceiling mount, so mount them on the ceiling. Generally in the central area to the area that's going to be covered. And within reason, you want to mount them as high as possible. That not only increases the coverage area, but it reduces the amount of obstructions that the RF signal has to go through, right? The higher up this AP is, the easier it is for that signal to go from your client device to the ceiling without having to pass through cubicle walls, people walking around, coffee machines, things like that, which are going to degrade the signal. So generally try to mount it as high as possible. Drop ceilings, from my experience, most drop ceilings, your standard white acoustic tiles, don't really degrade the signal that much. So if your building codes where you are allow it, you can simply put the access point, instead of having to drill holes in the drop ceiling and drop it out, you can simply lay the access point on top of the drop ceiling. So you can't see it, so you don't have to worry about your customers complaining about a dirty installation, and it's just sitting up there, and it provides good coverage. Now you want to put it centrally on the acoustic tile because the T-bars, which hold up your acoustic tile, are generally metal, and they will cause RF interference issues. Now, if you're mounting them up on a true ceiling, you just need to keep in mind that you want to try to avoid things that are going to harm the signal, right? So the ceiling's going to have, pipes, it's going to have air conditioning ductwork, it may have conduit for electricity. All of that stuff is generally metal, and metal reflects and blocks RF signal. So, you may need to buy and hook up standoffs that allow you to drop the access point down so it clears all of those obstructions. When it comes to hotels and things like that, we've got a couple just general rules. Now, historically, the way you provided coverage in guest rooms is you would mount the access points out in the hallway, and each access point would provide coverage from anywhere to 4 to 8 or 16 rooms, depending on construction and layout of the rooms. So that method of doing Wi-Fi is quickly going away. We call that umbrella coverage. And what we're moving to now is like we were talking about before in that smart antenna case study, is we are talking about putting one access point per room or one access point per every other room. And there's a couple reasons why you do that. One of them is in a lot of hotels, in the bathroom is generally bordering the hallway where the access point would be, so the signal is having to penetrate, fiberglass or tile walls. They're having to penetrate through the pipes and stuff like that. But the other thing is just how people use Wi-Fi has changed. When we first started doing guest Wi-Fi, it was mostly business travelers. They had a laptop, they would get in on the laptop, and they would check their email and send emails out. Now most people have at least 2 devices. Oftentimes they have 3 or 4 devices if you want to get on the Wi-Fi. If it's a family traveling, each person may have their own, phone, they may have their own tablet, they may have their own Kindle, that they want to get onto that Wi-Fi network. So they're overloading the access points. And then again, a lot of these cheap tablets that consumers have are not very powerful. So the signal has a hard time penetrating the walls and getting out to the hallway to where that access point is mounted. So the solution to all of that is put access points in the rooms themselves. Generally, you want some form of locking mount. It doesn't necessarily need to be a true lock, but something that's not obvious how to remove the access point from the mounting bracket so guests don't steal it. You may want to hide the access points behind furniture, again, to make it harder for people to notice it and steal it. And you want to be able to turn off the LEDs, especially if you've mounted the APs on the ceiling, because a lot of people have issues with those blinking lights interrupting their ability to sleep, and a lot of people get paranoid about what those devices are and think they may be cameras or some other spying device. I have been in places where I've gone into a hotel room and found the previous guest has wrapped a towel around the smoke detector because they were, not because they were smoking, but because the flashing light on it was annoying them or they were paranoid about it. When it comes to public areas, basically you want to plan each area independently. So you would plan for the hotel bar, separate from the lobby, separate from the meeting room, separate from the expo center, and approach each of those. And generally the main consideration is how many users are likely to be on the access point at a time. And so that's what you would use. How many users do we expect at peak times to be on that network? And then plan, how many APs you need to be able to cover that area for you. When you're setting up load balancing and client steering, if you can, again, you want to do it by area. You don't want to be trying to do load balancing and including guest room APs with lobby APs, because it can cause issues where the AP is trying to route people to something they physically can't get to. So if you can, you want to, set up load balancing and client steering rules so you're grouping APs based on the physical area. In anywhere where you've got a lot of users or you've got a lot of access points, smart antenna is going to make a huge difference in the quality of your network and can help you reduce the number of APs you need to install to cover that area. When it comes to schools, there's basically two questions. How many students are there on there that are going to be getting on the Wi-Fi? And is this a smart classroom? And by smart classroom, I'm referring to classrooms where teachers basically take over the screens. So each student has a Chromebook or a tablet that is connected to Wi-Fi, and the teacher, rather than broadcasting or projecting something on a wall or on a TV in front of the room, then instead transmits video or PowerPoints or whatever directly to every laptop. So if you've got something like that where you are streaming content from a teacher's computer to 20 or 30 or 40 students, you'll need a much more heavy-duty Wi-Fi deployment in the room versus just a standard room where the kids are maybe only getting on the Wi-Fi at the end of class for free study and checking Wikipedia. So that's something to take into account. And then, in general, students and teachers should be on different Wi-Fi networks that should be on different VLANs, right? So you want to make sure that kids aren't able to hack into teacher resources and vice versa. So in general, once you get up to about 20 students or bigger, you want to have 2 or more access points in the room. And then if you've got 30 or more students in the room, smart antenna makes a huge difference. And I also wanted to point out both our local area controllers and Nebula. We have a special algorithm specifically for smart classrooms that are designed to deal with, a bunch of students coming in as the bell rings and getting on the network all at once. So now briefly, I want to talk about Wi-Fi 6 because this is still a relatively new technology for a lot of people. It used to be known as high efficiency Wi-Fi. So a lot of these issues with Wi-Fi we've talked about today have been solved, or at least been improved greatly with Wi-Fi 6. Wi-Fi 6 was really focused on solving a number of these nagging problems that are becoming more and more prevalent as we get more and more wireless devices on access points and we increase the number of access points in areas. So that's where the high efficiency comes from, to better able to use the available airtime and to share it between devices compared to everything that has come before Wi-Fi 6. Another key thing here is Wi-Fi 6 works on both the 2.4 and the 5 gigahertz radio. 11AC only improved 5 gigahertz radio. The 2.4 radio is still based on 11N. So with Wi-Fi 6, you can have all of these improvements on both radios. It's specifically designed for dense environments here. Wi-Fi Alliance certification started back last year. However, the actual full standard from the IEEE wasn't actually approved until this year. And a lot of the products that were out there, especially the early Wi-Fi 6 products, are missing some of those key features. So I've got an example here using Qualcomm Gen 1 chips versus Qualcomm Gen 2. Same holds true for Broadcom and a lot of the other chipset vendors. And that is a lot of the early Wi-Fi 6 products are using these early gen chips before the IEEE standard was more stable and just before they had time to figure out how to implement some of this stuff. So they are missing some of the key features that differentiate Wi-Fi 6 from previous 11AC generations. Now, we saw some of this right with 11N. For those of you that are old like me, you might remember there was pre-N product and N-Lite product. With 11AC, we had Wave 1 and Wave 2. Unfortunately, with Wi-Fi 6, the industry hasn't been transparent about how they do things. So you will see a lot of products missing some of these key features, but they aren't going to tell you like we did in the past. They aren't going to say wave 1 versus wave 2 or light or pre or anything like that. They simply call it Wi-Fi 6. It only gets tested and has to support all these features if they get the Wi-Fi certification. So if a product doesn't have Wi-Fi certification, you don't know whether it truly supports all of the features or not. So that's something to keep in mind. Initially, it was just new products, right? These older products, the first Wi-Fi 6 products that came out a couple years ago that were using these chips. But what we've seen just with products this year is a lot of the cheaper Wi-Fi 6 products, to keep the cost down, are using these older chips that don't support the full Wi-Fi 6 feature set. And the only way really to know it is to check the data sheet and see if they mention some of these technologies. Do they mention upstream OFDMA? Do they mention upstream MIMO? Do they mention TWT and BSS coloring? If they don't, they may be the older Gen 1 chips. Another problem we've run into is with Ubiquiti with some of their Wi-Fi 6 products is they've only put Wi-Fi 6 on the 5 gigahertz radio. The 2.4 radio is still using 11N technology. So that is something you will see on the data sheet, but again, only if you check the specs. They don't, highlight the fact, hey, here's our Wi-Fi 6 AP, but it's only one radio, guys. So something to keep in mind. When it comes to Zyxel, all of our true business class products are Wi-Fi 6 Gen 2 chips on both radios, 2.4 and 5. So all of our true business class Wi-Fi 6 products are Wi-Fi 6 on both radios and support the full Wi-Fi 6 chipset. The only exception is our prosumer product that we just recently launched at Amazon, the NWA50AX. So it is missing a few of these Wi-Fi 6 features. It's using, I forget the chip now. It starts with an M. I forget if it's MTK or MediaTek, but it's using a chip, and it is missing some of those features. Everything that you would normally buy through distribution, the NWA 110, 210, 610, 510, 650, all of those are Gen 2 chips with the full support there. Another thing you may be seeing is now Wi-Fi 6E. We are starting to see more and more products supporting this. So basically, the FCC decided to open up some previously licensed spectrum in 6 gigahertz and open it up for unlicensed use. So products that support this will be calling themselves Wi-Fi 6E, the E for extended. So it opened up a huge amount of spectrum for people to use. So you've got 7 non-overlapping 160 megahertz channels versus 2 with 5 gigahertz. And obviously, if you're using smaller channels, you can fit a lot of devices in there without having to worry about co-channel interference. But again, the frequency has gone up, so range is going to be less. It's going to be much more easily absorbed by obstructions in the RF environment. But we've sort of run into the same situation we have with 5 gigahertz. There are already people that have been using for decades now 6 gigahertz spectrum that still want to continue to use it. So the solution that came in here was what they're calling automatic frequency control. They basically said we need to do something like DFS, but DFS caused too many issues. So automatic frequency control is how they are doing this and how they are playing with these existing customers who are already using 6 gigahertz. So it is less intrusive than DFS was, so it's going to cause a lot less issues as far as user experience goes. And again, the whole 6 gigahertz requires we support that, so you're not going to run into products that don't support it that are calling themselves 6E. And the Wi-Fi alliances, I believe, already started certifying products this year. We will have products that support 6E sometime next year. Something to keep in mind, though, when it comes to 6E is that some products will be dual band, some products will be tri-band. So some products you'll have to decide, which bands you want to support. Do you want to do 6 and 5? Do you want to do 6 and 2.4? Or maybe you bought a 6E product, but you've decided for that particular deployment, you don't want to use the 6 gigahertz, you just want to use 2.4 and 5. and some other products will support all three simultaneously. In general, those are going to be either bandwidth limited or they're going to require a lot of horsepower to be able to support maximum throughput across all three radios simultaneously. So something to keep in mind. And with that, we are done with today's webinar. If you have any questions, you can send them in with the question and answer interface. I'll stick around here for a couple minutes, but thanks for turning out, guys. I hope I didn't bore you too much here talking about Wi-Fi. My email's up there on the screen, Shawn R, SHAWNR @Zyxel.com if you want to reach out to me offline. And then also, if you weren't aware, we do have user forums, forum.zyxel.com. Unlike other user forums, our R&D and product management team keep an eye on there. Occasionally, we will decide to wade in and answer people's questions, but it's a good place to post up, feature requests and ideas, and know that they will be seen by people who can make differences. It's also where all of our announcements and release notes go first. So if you want to, keep on top of release notes or the latest security advisories, they will be posted to the forum before you will find them anywhere else. I am not seeing any questions coming in, so I'm going to go ahead and end today's webinar. Thanks for joining us, guys. I really appreciate it.